Hello everyone, my name is Finding Pepper, and welcome to How to Code a 3D Game in Scratch. Specifically, we'll be coding Minecraft over the course of this series. Although this series will be good for any 3D game you wish to create. This is a series, so we won't be doing everything this episode. This episode will be focused on rendering textureless blocks. Now, we will be using a method called raycasting. You may have heard of this. It's used to create 3D mazes and such, which are really just 2D games displayed as if they're 3D. However, it can also be used to make fully 3D games, which is what we're doing today. This is not the best or fastest method of 3D, but it is certainly the easiest, especially when it comes to displaying textures. So how raycasting works is we have a camera, and the camera shoots rays. And when these rays hit an object, they will record a pixel on a position of the camera screen. So you can see on the left we have what our camera sees, and on the right we have the world itself. Now this is a 2D representation, obviously. It's a 2D world projected onto a one-dimensional screen. You may be able to imagine this as a 3D world projected onto a 2D screen instead. It's just quite a bit easier to show with 2 dimensions. So if you've done parallax before, you can see that this is where some of the concepts there come from. As the object gets closer, it appears bigger, and it also appears to move faster when it's closer. Now you'll see that the camera only shoots rays a certain distance. This is the view distance of the camera, and each ray also has a certain amount up or down that it goes, and that amount corresponds to what pixel on the screen it represents, which I'll call the view x of the ray. So when it hits something, it will record a pixel at its view x in the camera view. If we would increase the FOV, the field of view, then these rays would become wider apart. So when we're deciding how far to move for each of these rays, we can multiply our view x by our FOV. Now we have one more value, which is our resolution, and that is the amount of rays we have. More rays means a higher resolution, more detailed, etc., but it's also laggier, so that is the balance there. We will also be able to move our camera up and down, and side to side. And you can see that as we move our camera, just a good thing to note that the object appears to move in the opposite direction of the camera. We can also rotate the camera, and then that will change the direction of the rays. You can see here that our view distance in view x will also rotate when the camera is rotated. So we need to move our rays based on the direction of the camera. So that's just another good thing to note. So hopefully with that you understand how raycasting works. Let us now talk about how we're going to store our 3D objects. We are going to use a grid. Now you may have done 2D tile-based games in which we have a 2-dimensional grid with a grid width and a grid height. Each of the tiles are stored in a list. The bottom left tile is at index 1, the next one is at index 2, and then 3 and 4 and 5. And the items at these indices of the grid list determine what tile it is, and also whether it's solid or not. Now once we get to the end, we can loop back around to the next row, and then count along here like that, 7, 8, 9, 10, 11, 12, etc. And then do the row after that and the row after that. Now for 3 dimensions, we just need to take this grid and we need to extend it along a third axis, which is the z-axis. And I haven't drawn the copies of the grid here, but you can imagine this grid being extended out along the z-axis. Alright, with that covered, let's get into actually coding this. I'm going to be using Turbo Warp, which is a Scratch mod which will compile scripts to make them run faster. I would highly recommend using this for the tutorial, as this will make things go much faster. You can just go to turbowarp.org, click See Inside. To save your project, you can click File and Save to your computer, and then that will give you a file which you can then load. Alright, so once you're here, let's start by adding our grid list. So make a list called Grid for all sprites. I won't be using any clones, so it doesn't actually matter that much whether our lists and variables are for all sprites or for the sprite only. However, we might have multiple sprites just to make the code a bit cleaner. But anyway, I'll delete my variable, make a new variable, grid width, grid height for all sprites, and grid depth. And I'll make these for all sprites. Now these will control the size of our grid. So when our flagged click, let's just set these to a number. I'll say grid width will be like 12, and then maybe have grid height be 8, and then grid depth be 10. You can make these all the same number, but it's easier to spot bugs if we make them different numbers. Now let's make a block called fill grid, and this will do what it says. It will fill our grid with empty values. So in this block we can delete all of grid, then repeat grid width times grid height times grid depth, which you can see is the total amount of cubes in our grid. Each time we'll just add a 0 to our grid, and 0 will represent air. We use our fill grid block when our flag is clicked. An empty grid is not very exciting, so let's make a block called place block, and then input block, and this will determine what block it is, and then at x, y, z. Run without a screen refresh. So here you'll see we need to find the index of this position in the grid. And to do that, we'll make another block, get grid index of position, and then input x, y, and z. Run without screen refresh, and then we'll make a new block called block index for this sprite only to hold the return value of this block. So I'll start by setting block index to 1. That's the first item in the list, and then we can change it from there based on our x, y, and z values. So let's change it based on our x value first. Real quick, let's make a variable called block size for all sprites, and this will hold how big our blocks are. I'll set block size to 16 at the start of the game. So blocks will be 16 by 16. So when I change block index, I'll change it by the floor, because we want it to be an integer, of x divided by block size. We're dividing x by block size to get sort of the grid x, and then as we see here, for every grid x, we change our grid index by 1. Now for the grid height, you'll see when we move up, we change by grid width. So after we change block index by this, we'll change block index by floor of y divided by block size times our grid width. Now for the z, this is similar. We'll divide z by block size, then rather than just changing by grid width, we'll change by grid width times grid height. So now that we have this block, we can code our place block. We can simply get grid index of position. We'll have our x, y, and z coordinates be in grid coordinates, so that means we need to multiply them by block size. Then all we need to do is replace item block index of grid with block. So now we can use this block when we press our flag. I'll place block, say 1 I guess, at 0, 0, 0. Let's place another block, block 3. I'll say 0, 0, and then 1 for the z. Then let's have a block, another block 1, how about? I'll put this at maybe 2, 1, 0. You can place these wherever you like. Now before we get to casting our rays, we need to code some scripts that will detect collision, because our rays need to know when they collide with a block. So I'll make a block called check collision at, and then inputs x, y, z. I'll make a new variable called collided for the sprite only, and this will store whether we've collided with something. So at the top I'll set collided to the empty value, meaning that we have not collided with anything yet. Now, one scenario where we know we will not collide with something is if x is less than 0, or x is greater than or equal to, we don't have a greater than or equal to block, but we can do that by just checking if it's not less than. So x is greater than or equal to grid width times block size. So that's the very right of the grid. If it is, we can just stop the script. We don't need to do any more collision checking. Now we can do the same for our y. So change the x to the y's, change grid width to grid height. Now for z, and we'll want to use our grid depth. Once we do this, we'll use our get grid index of position, x, y, z. And here we want to find more than just the grid index of the block, we need to find what block specifically it is. So I'll make a new variable called block for the sprite only, and in our get grid index of position, I will set block to item block index of grid. Now in check collision, we'll check if block is greater than 0. And if it is, we've collided with something, so we'll set collided to 1. Remember, 0 is our air block, and anything else is something that we should collide with. Now we're almost ready to cast our rays, but before we do that, we need to add our camera. So I'll make some variables: camera X for all sprites, camera Y for all sprites, camera Z, and then we'll have rotation variables for our camera as well. Camera rotation horizontal, and camera rotation vertical. If you think about if you're playing Minecraft and you move your mouse left, that would be changing the camera rotation horizontal, and then if you move your mouse up or down, that would be changing the vertical rotation. We'll set our camera X and Y to 0 at the start of the game, and then we'll also just set our camera Z to, say, like -50, so that we don't start in the middle of a block. And then we can set our rotation also to 0. I'll show these variables and turn them into sliders like so. Now let's look at casting rays. We won't be able to go the whole ray in one step because we need to be checking for collision periodically along the way. So let's say we move a mount each time we check collision. So we check collision, then move by a mount, then check collision again, etc. All the way until we get to our view distance. Now this shows how much we'll move in a single step of the ray. Again, here's the viewX variable I was talking about. This controls how far left or right the ray will be moving. This is assuming that the camera is pointing forward. Now let's say the bottom left of this is 0, 0. The top right of this is not too hard to calculate. It's just that we move up by amount and then right by viewX times amount. If we start at xy, we can just simply add x and y to these values. And again, this is only a 2D representation of this, just to make it a bit simpler to understand. Now, what if our camera is rotated, so it's not pointing straight forward? So this A here is the rotation of our camera. So to find this coordinate, let's take the approach we did before and start by moving forward and then move right. So first we want to find this coordinate here, which is straightforward for the camera. So to find this, let's take a look at the unit circle. Keep in mind that this is a slightly modified unit circle because in Scratch rotation, up is 0 rather than right. But anyway, we have our center coordinate 0, 0, and it's called a unit circle because the circle has a radius of 1 unit. Now to find the xy value of any given point on the circle, we can use our angle. It turns out that this coordinate has an x of the sine of A and a y of the cosine of A. You may have seen sine and cosine used before in other Scratch projects or tutorials. This is essentially what they are. If we want to move more than 1 unit, that's easy. We just multiply sine of A and cosine of A by the amount that we're moving. Now let's go back here. We can now put that value as our coordinate for straightforward for the camera. Now all we have to do is move to the right, like so, to find this coordinate. And this is a 90-degree angle. So we can just add 90 to A, and then take the sine of 90 plus A and the cosine of 90 plus A. I've put these on the left because they're rather long, but you can see they correspond to this final coordinate in, m. Awesome, so that's how we do it in 2 dimensions, but in 3 dimensions, moving straight forward is not so straightforward. So for 3 dimensions, we need to take a look at the unit sphere. So now we have our coordinates have 3 values, x, y, and z. And it's worth noting that we're saying y is up and down in this case. Now straightforward is over to here on the sphere, and then we can take our angle A, which is the camera rotation horizontal, and we'll use our unit circle equations of sine of A for the x value and cosine of A, this time for the z value, because we're not moving up and down at all in this angle. Now for our camera rotation vertical, We then have this point x, y, z, which is our final point, and the formulas for that are up in the top left. Awesome. Let's try to code this. We'll also go ahead and make those variables I mentioned in the beginning. View distance, and this can be for the sprite only. Resolution, FOV. I'll just go ahead when the flag is clicked, set resolution to 6, set FOV to 25, and set view distance to 100. You can of course mess around with these values if you like. Now finally, it's time to make our block called create camera view. Run without screen refresh. We'll put it in a forever loop after we set up all our variables. Then we have two more variables we need to create, our view x for the sprite only and view y. And I mentioned view x in those explanations, and view y is just because our screen is two-dimensional, not one-dimensional. And it turns out I lied, we actually have some more variables to make. As you saw, we're going to be using sine and cosine quite a bit, and those values are quite taxing on the computer to compute. Scratch has very poor performance, even using turbo warp, so it's better to compute those all at once beforehand and then not need to compute them again the rest of the frame. So our variables will be sine rot h, that stands for sine of rotation horizontal, and these will all be for the sprite only. Cos rot h, sine rot v, that's for our vertical rotation, cos rot v. Now, as you saw here, we'll also be needing to compute the sine and cosine of our angle plus 90. So make more variables, sine rot h plus 90, cos rot h plus 90, sine rot v plus 90, and cos rot v plus 90. Okay, that'll be it. That was a lot of variables, so we'll start by setting all these. And luckily it's pretty obvious what they each stand for, but of course you should always be wary of making little mistakes in your code, so just check it over to make sure you've got it all right. Our sine rot h will be sine of camera rotation horizontal, cos will be cos of that. Then for our vertical, sine rot v, sine of camera rotation vertical, then cos rot v, be cos of that. For our sine rot h plus 90, put a sine of this, and then plus 90. Make sure to put the plus 90 inside of the sine. Then same for our cos, then sine rot v plus 90, and then cos rot v plus 90. Okay, so we have all 8 of these set. Now we can cast our rays. We'll set our view y to negative 180, that'll be the bottom of the screen, and then we'll repeat for all of the rows, 360, and then we divide that by resolution. So this will mean that a lower number for our resolution variable will actually result in a higher resolution, which is a bit counterintuitive, but best to do it this way, so our screen will always be fully filled. Now we can do the same for our view x, set view x to negative 240, and then repeat 480 over resolution. Now within these loops, we'll change our view x and view y. So within the inner loop, that's our x loop, we'll be changing view x by resolution. So total, by the end of the loop, we've changed view x by 480. And then for view y, we'll also change that by resolution in the outer loop. So this is the loop that shoots all of our rays in the different directions. And the view x and the view y hold the amount up or down the ray moves. I think what we need now is a few more variables. X, Y, and Z all for the sprite only. And those will hold where we are in this ray. I swear, these are the last variables we're making for a little while. We'll set these variables to the position of the camera. So set X to camera X, Y to camera Y, and Z to camera Z. And then we'll make a block, look forward. Because boy, am I looking forward to coding this block. You know, I said we weren't going to make any more variables, but there's one that I forgot about. is called dist. D-I-S-T stands for distance. For this sprite only, this will hold how far along an array we are. Distance, so we'll set dist to 0 here, and then right after that we'll use our look forward block. So now we can repeat until dist is greater than view distance. And then we'll make a block, not a variable, a block, I swear, called move forward. And then an input AMT stands for amount. Run without screen refresh. Then I'll put this block in our look forward block and move forward by, let's say, resolution divided by 5. We want to make sure we're pretty precise in where the blocks are. And then we'll change dist also by resolution divided by 5. Alright, so let's start by just moving straight in the direction that the camera is pointing. Using those formulas I mentioned, we'll change x by amount times sine rho h times cos rho v. If you remember our unit sphere, these are just the formulas there. So here we'll change y by amount times sine rho v, and then z will change by amount times cos rho h times cos rho v. Alright, so after we move forward, we'll also want to move to the right, or left, based on our view x variable. So I'll start with the x, change x by amount, and then we need to multiply by view x. View x can be from negative 240 to 240, but that's certainly far too much to be moving in a single step of our array, so we'll just divide this by a large number, say 10,000. There we go. And also with an increased FOV, we want to move further to the left, or right. So we'll multiply this by FOV, by sine rho h plus 90, because turning 90 degrees horizontally will face us to the right. Now we actually don't care about our vertical rotation. No matter how far up or down we're looking, due right will always be in the same direction. And we will actually never change y when we're going due right, so we don't need to worry about that either. However, we do change z, so we'll just change the sine rho x here to a cos rho h. There we go. Now for moving up or down, that will be based on our view y. So we'll duplicate this and change the view x to a view y. And this will take into account our vertical rotation. So we'll just say plain old sine rho h, because we're not moving right anymore. We're moving straight forward in terms of our horizontal rotation. But for our vertical rotation, moving upwards, so we'll do cos rho v plus 90. Similar thing for our y, change y. Again, we don't need to worry about our horizontal rotation here, but we do need to worry about our vertical rotation. And this will be a sine of rho v plus 90. Then once more for our z, we'll just change this to a cos rho h. So we're multiplying by cos rho h times cos rho v plus 90. So this is our whole move forward thing. Now at the end of this, we can just check collision at x, y, z. And here it's better to round these values. It'll just make our 3D view look a bit nicer. Now back in our look forward block, after we move forward, we'll check if collided is greater than the empty value. If it is, we can simply stop the script. Now let's go back to our create camera view block. We'll need to create a list to hold this so-called camera view we're creating, and I'll call it view. You can make it for this sprite only. This list will hold data about each of our pixels. So at the beginning of create camera view, we'll delete all of view. Now after we look forward, we can check if collided is greater than 0. And then we'll add our view x to view, view y to view, and that will be it for now. And you'll see there are 2 bits of data for each pixel of our view. So I'll make a variable called data amount per view pixel, the sprite only, and this will simply hold that value of 2 because there's 2 things for each view pixel. We can set that at the beginning, set data amount per view pixel to 2. Alright, and now we need to create a block to display this view, and I'll call it display view, and run without a screen refresh. I'll use it in our forever loop after we create our camera view, each frame. Now we're going to use our pen to draw this, so I'll add the pen extension, and start by erasing all, just to clear the screen. We'll then set our pen size, I'm going to do this based on our resolution. I'll set it to resolution times 1.2. A more detailed resolution will result in a smaller pen size. Now we're going to be needing to loop through our view list, so I'll make a variable called I for the sprite only, and that will hold our position in the list. Start by setting I to 1. Repeat the length of view divided by data amount per view pixel. And each time we're change I by data amount per view pixel. We can then go to an X of item I of view and a Y of item I plus 1 of view. So this I is the index of the list, and then for each of these pixels, we'll go to their position, then pen down and pen up. So just draw a small circle there. And one more thing, in our get grid index of position XYZ, we need to move where the floor is. I'm sorry about that. We need to make sure the floor is of Y divided by block size, and then we multiply that by grid width. Then the same for the Z divided by block size. Alright, now we can run it. We can use our sliders to move the camera position. You can see these are the blocks that we placed, and those are looking pretty good. Let's see if rotating horizontally works, and it appears to. And vertically also seems to be working. Now it's definitely pretty laggy. Later on we'll be doing some optimizations to try to make it slightly less laggy, but for now let's just leave it like this. Let's go ahead and add some camera movement, as in controls for our camera movement, so we don't have to worry about these sliders. We'll make a block called move camera. Run without screen refresh, and I'll stick it in our forever loop right at the top before we create our camera view. Let's start by changing our camera rotation. Change camera rotation horizontal by key right arrow pressed minus key left arrow pressed. Because these Boolean values result in a 1 or a 0 when they're put into a number input, this will return 1 if we're pressing the right arrow, -1 if we're pressing the left arrow, and 0 if we're pressing both or neither. Now we can multiply this by 5, say, to make it a more substantial value. Then we'll do the same for the vertical rotation, changing the right arrow to an up arrow and the left arrow to a down arrow. I'm going to limit the vertical rotation. If camera rotation vertical is greater than 90, we will set it back to 90. And if it's less than -90, again we'll set it back to -90. Now we can change our camera X based on the direction we're facing. So let's start with some forward and backward movement. We'll change camera X, and then we'll get one of these key press checks again. Change it to a W and an S for forward and backwards. Then we'll multiply the camera X1 by sine of our horizontal camera rotation, and then camera Z will change by the cosine of this. For moving right and left, we'll change camera X by D minus A, D is right, A is left, times sine of camera rotation horizontal, and then this time we will add 90 to it. So we're moving right. Then we'll change camera Z by this times the cosine of that. Then for our camera Y, I'm not going to worry about direction. We'll just use the E key to go up minus the Q key to go down. Let's run this, see if that works out well. Try pressing our keys. That seems to be working just fine. Let's try with our rotation. Okay, good. So that's looking good. We can hide these variables. And yeah, now we can just fly around our world. You can see when we get farther enough away, our blocks will begin to disappear. And again, we'll work on improving the lag a bit more later. For now, if you just turn down your resolution to say 10 maybe instead, then it will run much faster. You'll see there's these little squares in between our pixels as well. Those occur because our pen can only draw circles, not squares. So if we want these pixels to be fairly exact to the size which they are, then they'll need to have little pockets between them. If you want to remove those pockets, you can go into our display view and set pen size to a higher number. Keep in mind that in Turbo Warp, because this compiles things into JavaScript to run faster, we need to press the flag again for any changes we make to be updated. So resolution times 1.4 for our pen size seems to work pretty well. But again, it's up to you, whatever you like. Now looking at this again, it's kind of hard to tell what faces are what, like what we're looking at. Maybe we're just looking at a big blob of blue dots. So let's change it so that the different sides of our cubes have different shading. I'll create a new variable called brightness mod. This is a modifier for the brightness of our cubes. To tell what side of the cube we are hitting when we move forward, we need to move by X, Y, and Z separately. Whichever direction causes us to collide with the cube is the side of the cube that we're on. So first we'll change X, then check collision at our position. Then if collided still equals the empty value, then obviously we haven't collided with something, so then we move Y. Then we check our collision again. If collided is still the empty value, we'll move X, and we'll move Z, and then check our collision once more time. Then we can make these an if-else actually, and set our brightness mod in the else if we do collide with something. So for X direction, let's set brightness mod to -10. For our Y, let's set it to 0. And for the Z, we can check just if collided is greater than the empty value, in which case we'll set brightness mod to -20. Then back in our create camera view, we'll also want to add brightness mod to view. And in flag click, that means we'll need to set our data amount per view pixel to 3. And in display view, we can set our pen color. And then here you can choose whatever color you want. So it'll be what color the cubes are. And then you'll change pen brightness by item I+2 of view, which is the brightness modifier. Let's run this. And we can see that the different sides of our cubes are different shades of our blue color. Awesome. Okay, this is much more recognizably 3D, I would say. It's still pretty low quality and laggy, but raycasting is unfortunately just not a very fast method of 3D. That's alright though. We will be doing some optimizations later on, because this is all for this episode. We have successfully created a 3D renderer, and we will, in the coming episodes, be turning this into a game like Minecraft. Or if you feel so inclined, you could turn this into a different game. But anyway, that will be it for this video. I hope you enjoyed this video. Maybe leave a comment, or, you could even subscribe. Just saying, that's an option. And make sure to stay tuned for episode 2, which should be releasing next week if everything goes to plan. But anyway, I'll see you next episode. Have a great rest of your day, and goodbye!